Hi to Franco.
Hello. Can you
Hello.
hear me?
I can. Great to have you on the stage.
Yeah, thank you very much for allowing me to speak to you today.
No, it's a pleasure. So Franco
Egidi?
Egidi
Yeah.
is GD is with Software for Chemistry and Materials, SCM, the company, and he'll be telling us about atomistic multiscale simulations of OLED materials. So I think your slides are preloaded, which is great. And whenever you're ready,
Yeah, of
please.
course. We can start right now. So before I go into the details of the presentation, I would like to give you a little bit of background on who we are. So we are a small chemistry a software company based in Amsterdam. There was an offshoot of the Free University here in Amsterdam, and we specialize in building software for chemistry simulations of all kinds. So we do anything from simulating spectroscopic properties of molecules to from very small molecules to very large ones, transition metals, to bulk materials. So polymers, semiconductors, metals, everything, up to also liquid mixtures, thermodynamics. So all kinds of chemistry simulations. And because of this, we thought it would be ideal for us to tackle a problem like modeling OLED materials, which have various scales of complexity from the molecular to the device one, uh, which really need expertise on various kinds of physics and chemistry involved. And so first thing first, so OLED devices, these are extremely complex but also common devices which are present in everybody's phones and screens, and they're becoming more and more popular by the day. And really, they are a marvel of technology which really takes advantage of many different phenomena, and therefore they are quite complex to model and research. Now, they usually consist of a solid state thin organic semiconductor between electrodes. So the electrodes feed in the current, and you get your optical response. Of course, one of them has to be transparent for you to actually see what's going on, and the properties and the response of your device really depend on the really fine interactions that you have within. And you can see in these schematics really the different scales involved. Now, how would you ever even begin to model something so complex? So the approach we chose is multiscale modeling. So we just split the system into different layers and then different levels in terms of size and in terms of time scales, as well as the level of physics and chemistry involved. And we really want to model these devices from an ab-initio level all the way to the device level. So we start from the very fine electronics properties of the molecules present within the device. We use those to simulate and model the structure of the device itself, of the organic semiconductor layer, and then use the information we gather from those simulations to further calculate the response of the device in terms of what you actually see and what you need. Because of this, it is quite complex to build a system and a workflow that actually integrates all of these calculations with each other and uses the results from one to perform the next. So that was our goal and our challenge for this project. And I'm going to show you what we were able to come up with. So, like I said, you start from your molecule, you model your material, you then build your stack, which is really what constitutes the device itself. And that gives you the pixels, and which then generate the image that you see on a screen. So ideally, for these type of simulations, we split the workflow into two different stages. So a molecular level, where we really go in and model the atomistic behavior of the device, and it is really composed into two phases itself. A phase where we model the morphology and really build the stack of the molecules itself, and then a phase where we calculate the electronic properties that you need using quantum mechanics. And then we have a device level simulation layer where we use the informations we just gathered to calculate the response and what you really